Okay, in this video I'm going to talk about the equilibrium quotient. The equilibrium quotient is a way that we can determine whether the equilibrium is in a position where it's going to shift to the right, creating more products, or to the left, creating more reactants. We have two basic options here. So the idea here with our typical equilibrium constant K, we have the concentration of the products over the concentration of the reactants. And this is at equilibrium. The equilibrium quotient, Q, takes the same equation for products over reactants, but instead of looking at these concentrations at equilibrium, it looks at them at current condition. What we can then do is we can compare Q and K. If Q is greater than K, then we have too many products. See, the products are on the top. So if it's bigger, that means we have too many of these guys. I'll call that case 1. And this is 1 here. If there are too many products, that means the equilibrium shifts to the left, creating the backward reaction is favored, and that means more reactants are created to use up the too many products that we had. Alternatively, if Q is less than K, that means that our denominator is too big. That means we have too many reactants. We'll call that case 2. There are too many reactants. The equilibrium will shift to the right. The forward reaction will be favored, and more products will be created. So we use the same basic formula as K, but with Q, we use the current conditions. There is a third case. I guess it's possible that Q could be equal to K, which would mean that we are already at equilibrium, and we would expect no observable shift. So in general, if we had this expression, and we would have said K was equal to the concentration of Y to the power of C, assuming all of these are gases or variable in some way, and Z to the exponent D over W to the exponent A, and X to the exponent B, this K expression would be this at equilibrium. Q does the exact same thing, but at current conditions. So basically, you're comparing your current conditions to the conditions you expect at equilibrium to see if you have too many products or too many reactants. Here's an example. The following system initial concentrations are given in this chart below. The equilibrium constant, K, for this reaction is equal to 0.048. I just made that up. Determine if the system will shift towards a product of reactants when reaching equilibrium. So first of all, we're going to notice that all of these are gases. So we're going to write what would usually be our K expression, but this time we're going to call it our Q expression because we're going to use our current concentrations with it. Our products are just the SO3, and it is a coefficient of 2, so we make it squared. And our reactants, SO2 squared and O2 to the power 1. And then we have our current conditions. So we have 0.082 molar SO3, and that's all going to be squared. And we have 0.12 molar, and that's squared, and 0.1 molar, and that's just left alone. So let's just punch all these into a calculator. 0.02 squared divided by 0.12 squared divided by 0.1, and I get 4.67. So my Q is much greater than my K. That means my numerator, or my top part, is too big. Or you can say your bottom part, or your denominator, was too small, which means we need the products to go down because they're on top. Or you could say we need the reactants to go up because they're too small. What that means then is for this reaction, the backwards reaction will be favored. And if we were to try and consider what the change in this reaction would be, we would say that this is going to decrease. For every, we got to be careful of our mole ratio here. So if this decreases, we want to say this is going to increase, and this is with a 1. So we'll just make that an increase of x. This is going to be a decrease then of 2x because there's 2 of these for every 1 of these. And then this will be an increase of 2x. So this equilibrium is going to shift this way. That's how it's going to change in order to try and get its Q to equal its K. So that's how you can use an equilibrium constant to predict which way an equilibrium is going to shift. Later, when we're doing examples where we're predicting which way or what the concentration of something at equilibrium is, this will be a useful tool for us to predict whether this should be a positive x on this side or a negative x on this side, depending on which way the equilibrium is changing.